In this video, we will look at one of the classics from the two-pointer world. So you are given a string and you have to find out the number of substrings that contains exactly k distinct characters. And you know that a string usually contains characters from A to Z. So the value of k that could be given as an input could be any number from 1 to 26, and you have to solve it for each different k. Now, how do you solve this problem with a correct but maybe a slow solution? So you can do that by considering that there are O of n square substrings. So you can iterate over each of the substrings, and suppose the substring that you are currently investigating is this one. This is the left endpoint and this is the right endpoint. Then you can iterate over all the elements of this substring and figure out if the number of characters in this substring from L to R is exactly equal to k. If it is equal to k, you increment the count by 1. But the problem with this approach is that since there are O of n square substring and you have to iterate the substring again to figure out the number of unique characters, that becomes O of n cube. So can you do it something better than O of n cube? So yes, you can do that using a very standard trick, which some of you might know, some of you might not know. So what you want to find out is how many unique characters are there in a substring from range L to R. So how do you convert this uniqueness to a known territory? So you can apply a famous trick where you take advantage of the fact that all the characters are between A to Z. So let's maintain 26 different arrays, each corresponding to a unique characters. So for A, we maintain an array of length n, same as this one. Length will be the same. For B also we maintain another array. For C also we maintain another array, and I'll talk about what these arrays would contain. So this is B, this is C. Then you look at your original string, and if it had A at this position, A at this position, and A at this position, so the array that you create, that will be a binary array which only contains zeros and ones. So you add a 1 at all the locations, at all the indices that A appears, but you add a 0 at all the other locations. You repeat the same thing for B. So suppose B appears over here and B appears over here. So you add a 1 at each location that B appears. So you will add it right after 1 over here, after A, and you will add it also over here. So in this manner, let's see how we can utilize these 26 arrays, because the number of such arrays can only be limited by the number of unique characters that can possibly exist in the string, which is 26. So how do you quickly find out what is the number of unique characters in a particular substring? So you can do that by converting this uniqueness to frequency. That is, let us count the frequency of each character in the substring. And how could you do that? There is also another trick for that. You can apply the prefix sum trick to compute the sum of a subarray in O of 1. So with this prefix sum trick, from the first array, you can quickly tell how many times A appears. You can quickly tell how many times B appear. You can quickly tell how many times C appears. So if you repeat this operation 26 times, you will know exactly how many times A, B, C up till Z appears. Then all you have to do is simply check frequency of which elements are positive and you count them. So if frequency is positive, like if it is greater than 0, it means that that element appears in your substring. So you count how many elements have frequency greater than 0, and that count is your unique characters count. And in this manner, you won't actually have to iterate this big subarray. You can only just iterate this 26 different arrays that you have created. And in this manner, you will be able to solve the entire problem in O of n square. So this is a very famous trick, nothing new about it. I'm just adding as a refresher. But now what if you want to solve it in even better time complexity? Can you try to solve this problem in O of n? So right now you can see that enforcing the constraint that each subarray should contain exactly k distinct characters is a very difficult problem to solve. So let's solve a weaker version of this problem where we say that, okay, I don't want exactly k distinct characters. Can I simplify this and I ask a weaker version, which is given a particular value I, tell me how many subarrays are there such that they contain at least I distinct characters. I don't need exactly I need at least I distinct characters. But how will this help us? Because if you were able to compute this f of I, then do you have any algorithm to compute the answer to the original problem with exactly k distinct characters? Yes, you can do that by utilizing this fact that f of I means how many subarrays are there which contains at least I unique characters. So if it is at least I, it could either be I or I plus 1 unique characters or I plus 2 unique characters and so on. But what would f of I mean? F of I plus 1 mean? So f of I plus 1 would mean the number of subarrays with at least I plus 1 unique characters. So this means it could either be I plus 1 unique characters or I plus 2 unique characters or I plus 3 unique characters and so on. So now notice any substring that has I plus x unique characters where x is strictly greater than 0, that will be counted here as well as here, because if something is for example, if I plus 2, so I plus 2 is at least greater than I and also at least greater than I plus 1. So this means it will be counted here and here, and the the number of times that you count it over here will be exactly same as the number of times that you count it over here. So now if you look at this quantity f of I minus, sorry, if you look at this quantity, yeah, f of I minus f of I plus 1, what would these represent? So you see that all the numbers that are common in both of them will get eliminated, and whatever will remain, this number would represent how many substrings are there with exactly I unique characters in them, and which is exactly what we are looking for. So our answer would be simply f of k minus f of k plus 1. So, okay, now we know that if we are able to compute this f fast enough, then we will have our answer. But how do you even solve this version of this problem? Because it's not at all obvious to see the solution of this version where you want your substring to contain at least I distinct characters. Now that you have concluded that if you can solve this version of this problem, then you can also solve this version of this problem. But how do we compute f of k efficiently? Because this also does not seem to be an easy task. So in these kind of problems, we usually fix the starting index of the substring that we are looking for. Suppose this is f of I, and that is why you will notice that I have changed the notation from f of I to f of k so that you do not get confused, because this k represents a fixed value that we are looking for, and this is the capital K, which is the answer to the original problem, and this I am reserving it for the index of the elements that we are dealing with. So now you are interested in finding out how many substrings are there that start at I and have at least k unique characters. But how do you find that out? So in order to find out all the substrings that start at I, you have to at least find the first substring that start at I and has k distinct characters. So suppose this is the first substring that starts at I and has k distinct characters. In fact, let us formalize it like so. You define let's define dp of I is the minimum R such that the string I till R has at least k distinct characters. You are looking for the minimum window that satisfies this condition, because if you are starting from here, and if this is the minimum window that contains k distinct characters, then if you are evaluating this subarray, of course this subarray will not contribute to the answer because it doesn't have at least k distinct characters. So the arrays that you are creating, that can only be towards the right of it. So now let's see how do we efficiently find out this DP value for all the indices. So this is our DP definition. Now notice what happens. So for this particular index I, suppose you have concluded that this is the R in which there are at least k distinct characters. Now let's look at the DP value of I plus 1. So for DP value of I plus 1, notice that for this window from I to R, you had k unique characters. So for what can you conclude about the DP value of I plus 1? So you have to stretch this string that starts from I plus 1, and you have to keep going right until you find k distinct characters. But now notice that if I had to stretch as far as R to find k distinct characters, would you stop before R? The answer is no, because if I had additional help, so you have all the, suppose this is I and this is R. So I had to stretch from here till here to find k unique characters. So our claim is that when you start your journey at I plus 1, you cannot stop early. Why? Because if you stopped early means you found k unique characters. So I would have also had the benefit of this section, because all the substrings that I was evaluating, it was starting at I. So whatever you are doing, I is doing a superset of that. So this means that you have to go at least as far till R and then maybe some more. Why maybe some more? Because one element of that substring was taken away from you, because I has now been deleted. So you are now starting your journey at I plus 1. So if I was the sole unique character in this window, you might have to go even further. So what can you conclude from here? So you can conclude that all the DP values would be sorted. So let's write down that conclusion. You can write down the conclusion that all DP values are sorted in non-decreasing order. Mean DP of I is greater than or equal to DP of I minus 1. So this means that if they are actually sorted in non-decreasing order, then if you be smart about it, about the order that you want to populate the DP, then you can actually achieve an O of an algorithm. So how do we populate that DP? Let's look at the algorithm for that. So for suppose for I, you start your journey over here. In fact, let's populate it like so. You start from here. Let's populate DP of 0. So for DP of 0, this is the index 0. This is the index 0. And you start from here and you keep going right until you have found k unique characters. So suppose you end your journey over here. And let's also maintain in a map. Let's maintain a frequency map. So this is your frequency map, and you maintain that for the 0th element, for the I is equal to 0 case, in this frequency map, you maintain frequency of all the 26 characters of the alphabet from A till Z, and you record that in each window, in the first window that you encounter, how many times did you see A and how many times did you see Z, and all the elements in between as well. So this part you can do via brute force. So you start from here and then you keep going around, right? And then you find your R that you are looking for. But now notice that when you have done all of this expensive work, you don't have to throw away this frequency map that you have created for this window. Why? Because this window can only shrink from here. Now when you start your journey at I plus 1, you will not get the benefit of the character that was residing over here, but another copy of the character could already be present in this window. And if that is the case, then the minimum R at which I plus 1 to R becomes k, at least k unique characters, is the same as the one that you encountered with 0. Otherwise, if it was the sole unique character, then you have to move right a bit. So how do you determine this fact? You can simply look at the elements of your frequency array, and when you move I to I plus 1, so this is I plus 1. So when you go from I to I plus 1, you simply decrease the frequency count of the character that you just migrated from. So whatever character is present over here, you make it 1. And then you see whether you still have k unique characters in your map. If you don't, then you keep on increasing this R even further, and suppose you keep on getting all the copies that are already available over here, you keep going around, right? And you finally reach here, and this is R2, let's say this is R star. So this R star, this means that for this I plus 1, this R star is the first point where you achieved exactly k unique characters, right? Because here I'm saying that minimum R with at least k distinct characters. In other words, you can say that my DP definition is nothing but my DP definition is DP of I is the minimum R such that I to R has exactly k characters. You could say it like so, because you want at least, but then you also want the minimum R, so that is at least k characters, and both of these definitions are equivalent. So in this manner, you can find out what is the DP value of I plus 1, and once you have done that, you migrate from I plus 1 to I plus 2, and when you do that, you remove one occurrence of the element at this position from your map, and if your number of unique characters had gone down from k to k minus 1, then you keep increasing your right pointer, and then as soon as you add one element in your right pointer, you increment its frequency in the map by 1. Now you can see that your right pointer only moves to the right, and we already said that the DP value would be sorted in non-decreasing order. So this means that in O of n, you can populate all the DP values. So if you can do this, how do you find the answer to the original problem? Like, not the original problem, but the modified problem, where we wanted to find out how many substrings are there that contain at least I unique characters, right? Or at least k unique characters. So how do you find it out? Again, all the substrings that you are looking for, it should have at least k unique characters. So it can start at any index. So let's say that it starts at index I. So if it starts at index I, where is the first position that it can end? It can end at DPI. And this is why we had defined this DP definition in the first place. Because what does DPI mean? DPI mean that what is the minimum R in which this window will start containing exactly k characters. We said at least k, but that is equivalent to saying at exactly k. So this means that the string will start at I, but it can end at DP of I, but it can also end at DP of I plus 1. Why? Because at DP of I, you have achieved at least k. So there is no harm in extending the string even further. There is no harm at all. But if you end early, then you know that this dp of I is your minimum r. So if you end early, for sure you will not get the total count of characters as at least k. So your answer would be, your ending positions could be what? If you count zero based indexing, your ending positions could be n minus 1, n minus 2, n minus 3, up till you could end your journey at dp of I. So if you wanted to find out how many substrings are there that contain at least k characters, you can find out the number of substrings that start at any index I for all index I that are available in the array, and they can end over here. So how many numbers are there in this range? So the total number of elements that it can end at is n minus 1 minus dp of I plus 1. So the number of elements in the range a to b is equal to b minus a plus 1. So this and this cancels out. So this number is nothing but n minus dp of I. So you have to take the sum of this n minus dpi, and this will give you the number of substrings that contains at least k characters, which is nothing but f of k. And the answer to the original problem is f of k minus f of k plus 1. And this way we have solved the entire problem in O of n. And this might be a very standard trick known to some of you, but I still decided to make this video because not a lot of people, especially a lot of newcomers to code forces or lead code, they might not be aware of these tricks where you where if you wanted to find some properties of a substring, then you first formalize it by saying that, okay, I want my substring to start right here at a fixed index I, and then you define your dp like that. And then you utilize this two pointer theory that all the dp values would be sorted. So if the first substring spans till here, then the second substring, if it starts at I plus 1, you already took away some element, so you have to expand it even further. And then finally we applied the trick that if you have the answer for at least k, then you can get the answer for exactly k. That is a very standard mathematical trick. So if you want to submit this problem, I will link down the problem in the YouTube description.